Calculus and its applications in scale-free networks, written by the following authors, published on 17 to 18 November by IEEE. This paper contains 6 pages. There are many different systems in the world today. Some artificial, like the internet, others natural, like our social networks. These systems can be represented as complex networks, containing nodes and vertices. Nodes are the elementary units of the systems, and the vertices connect nodes to each other. From the last decade, in complex networks research, the scale-free nature property has been seen and observed in many complex networks, such as social networks and technological networks like the internet. So what does it mean when a network is scale-free? It means it has growth and preferential node attachment, which we will talk about later. Researchers continue to look at real-world systems in terms of having nodes and links, aka as complex systems, to better understand their behavior and eventually simulate real-world systems. The research on how scale-free networks evolve revealed a phenomenon called preferential attachment, which shows the concept whereby nodes in a network that joined early have more chances to acquire many links in the network. This can be seen in this diagram, also known as the Barabasi-Albert model, which shows how the new nodes attach to well-established nodes as the network grows. However, the BA model, which assumes that the probability that a node gets connections is dependent on the time which it was established, fails to weigh the importance or fitness of the node. What do we mean by this? Applying it to the real-world context, when research papers get information and quote citations, a better scientific paper is more likely to be quoted. From this, we can see that the fitness of the nodes is more important compared to the time that it was established. The BA model and fitness model can be constructed using calculus, which will be further discussed next.
According to the BA model, after t time steps, the number of nodes is given by t plus m, and the number of links is given by mt plus e. Let us now understand and implement calculus concepts to scale-free networks. In the geometric sense, differentiation is the slope or gradient of a curve. From a physical view, it is the rate of change. Here we show how node degrees evolve with respect to time by using differentiation. The concept of preferential node attachment can be described as the rate of change. For example, we can say the rate of change of node attachment with respect to time or any other independent variable or factor. Say, for instance, n represent any node in a complex network, we can observe how that node varies during different time intervals with respect to time by acquiring or grabbing new nodes and links entering in the system. Through differentiation, we can calculate the time dependence of the degree ki of a given node I. This degree of node increases every time a new node enters the system and links to the node I. Next, let's move on to the definition of integration. Integrals are essentially antiderivative. For each of the new m connected edges, the probability p or chances of linking to an existing node I is given by, here n is the number of nodes present in the network and the change in degree will be calculated as n. The change in the degree can be further written as, now if n is large, by approximation, solving by separation of variables, on integrating both sides and using our basic knowledge of integrations of inverse function, we get, here c is the constant of integration. To solve the equation, we use the initial condition. Putting back the value of c in the equation, we get this final result, using which the researchers were able to get the final result, which can best describe the growth process in real-world complex networks. This mathematical approach can help in computationally simulating complex networks for our better understanding on how they evolve and their future growth.